class. So
Sir?
I have shared my screen now. So hopefully you would see it in a couple of seconds. So in the last class, if we can recap quickly that in the last class we discussed, or in fact the last chapter, which is chapter number 7, we discussed about dimensional analysis, similitude, and modeling. So basically, this chapter is related with the experimental fluid mechanics. So it means that if we need to conduct experiments, first of all, we need to come up with dimensionless products which are called pi terms. And for that, we discussed two methods. One was method of repeating variables, and then the other method was method of inspection. So, and then when it is difficult to conduct the experiments on the actual system, then we create a model, which is usually the scaled down model, and then we conduct experiments on that model, and then we can correlate the results of model and actual system by the similitude study, which we discussed in the last class. So, if you remember that the major essence of that was that each pi term of actual system should be equal to the corresponding pi term for the model. So only then we can translate the results which were obtained for the model, that can be translated back to the actual system. And in the last class we discussed about the example of drag force on a rectangular plate, and then we saw that how we can because in the experiment we are going to get the value of dm, which is the drag on the model, and we need to calculate the drag on the actual plate. So that we can do by considering the similitude between the model pi terms and actual pi terms. And then in the last class we also performed several numericals, and I gave you an assignment which is due, I think, on this Friday. I'm not sure about the deadline. So anything you want to ask in this chapter before we start the new chapter? Anything which is not clear, anything you want to add, so you can just tell me now, otherwise we can start the next chapter, which is chapter number 8.
सर एक चीज कंफर्म करनी थी.
Yes, please. जी हसन मुस्तफा बताइए.
यस सर, काइंडली ये कंफर्म कर दें कि हम जो रिपीटिंग वेरिएबल्स हैं वो कोई भी ले लें तो आंसर जो है वो हमारे सेम आने चाहिए.
रिपीटिंग वेरिएबल कोई भी लेने का मतलब ये है कि उसके अंदर ना दो तीन उसकी थी कंडीशन. अगर मैं आपको स्लाइड पे ले जाऊं, रिपीटिंग वेरिएबल जहाँ पे सिलेक्ट करते हैं ना, उनकी दो तीन रिक्वायरमेंट है. यहाँ पे अगर देखें ना, स्टेप नंबर 4 लिखा हुआ है, select a number of repeating variables where the number required is equal to the number of reference dimensions. So reference dimensions are basically the basic dimensions which are needed to describe those variables. So usually they are 3. So it means that in most of the cases the number of repeating variables are 3. Now, if you look here, that if you see here that we have got 3 points here. First of all the required reference dimensions should be included within the group of repeating variables. So it means that whatever repeating variable you are choosing, all the 3 dimensions should be covered by using those variables. Which means that, for example, I give you an example for this, that in this problem, where we were studying the drag force on the on a rectangular plate. So if you let me take it here, we can take. It's up to us that if we take W and H as a repeating variable. Now we all know that W and H, they are having the same unit. So they are not dimensionally dependent. And in the third, we take velocity. So it means that the repeating variables we choose, that are W, H and V. So it means that we are missing on one parameter, which is force unit, because W and H, they are of unit of meter, and velocity is meter per second. So there is no force dimension in this. So it means that we need to take either mu or rho as a repeating variable. Only in those variables we have got the force dimension, right? So that was the first point. Second point, which I have explained earlier, that each repeating variable must be dimensionally independent of the other. Mr. Mustafa, do you get this? That we cannot select W and H for that problem. Do you understand that?
Yes, sir.
Okay. And the third one is, the dependent variable is not usually chosen as repeating variable. It means that if the drag force is the dependent variable, the variable which is on the left hand side of the functional form, that is the dependent variable. So that is not usually chosen as a repeating variable, because we only need one pi term on the left hand side for that, right? Because we are going to conduct experiment to determine that variable. So it should only appear in only one pi term, which is on the left hand side. So if we can meet all the three conditions which are listed here, then we are free to choose any variable. Like here in this problem, we have chosen d, v, and rho. So we would get the same result if we choose the variable d, v, and mu. So the pi terms would be the same. Same means that the denominator can be replaced by the numerator, but it doesn't matter because they are non-dimensional, so you can easily inverse that. So, do you understand? Like in this problem, when we chose dv and rho, so we got the pi term, which is mu upon dv upon rho, right? So we know that dv rho divided by mu, that is Reynolds number, so we can easily inverse it. So in fact, if you choose dv and mu as repeating variable, then you would get rho vd upon mu. That pi term is equally correct. So pi terms are usually unique. It doesn't depend upon the selection of repeating variable. Is it clear?
Yes, sir. Thank you, sir.
Okay. So thank you for asking this. So in a way, we just recap the most critical portion of method of repeating variable, which is the selection of repeating variable. So once we do correct selection, and then it is kind of very systematic way of determining the item. Now we move our attention to the next chapter in your book, which is chapter number 8. So the chapter we have covered, we have finished right now. That is chapter number 7. Now we are going to cover chapter number 8, which is viscous flow in pipe. So it means that we are talking about internal flows. So as you know that in the beginning of this fluid mechanics course, in the very first lecture, I gave you an introduction that there are two types of flow. One is internal flow and one is external flow. So external flows we are going to cover in chapter number 9. So first we will cover viscous flow in pipes. So that is internal flow. So where do we find internal flows? There are many applications of internal flows, like all the heat exchangers, like boiler, turbine. They require some kind of piping. right? So because we usually bring the fluid inside the pipe and then we heat it in the boiler from outside by burning some coal or burning some gases, and then your geyser installed at home, and then what else? Uh, when we talk about human body, all the blood is flowing through veins, so they are also kind of internal flow. Then the flow through your trachea and bronchiole and human lung, that is also kind of internal flow. So we have got very vast application for internal flow. So transportation of fluid includes conduits like oil, oil pipeline, gas pipeline, which is coming from sewage, and then we have got engineering application like boiler, condensers, then home application like home geyser, evaporators, then oil, gas, water pipelines, air conditioning, and ducts. Okay, so we are pretty confident that there are quite a few applications where we. So that's why we are studying this chapter, chapter number 8. Okay, so geometrically, internal flows has got two types. One is geometrically, we say that one is pipe. So in pipe flow, we have got a circular process, right? And then the second one is duct, right? So duct is something like square or rectangular cross section. So yes, Ahmed Aziz, anything you want to add? Okay, maybe it was my by mistake, so that's fine. So okay, so we were talking about pipe and duct. So usually pipes are used when we have got an application where the inside pressure of the fluid is very different from the outside pressure. So it means that the pressure difference pressure difference between inner and outer side is very high. Like if the flow is coming from a pump and the pump is creating very high pressure at where it is installed, so it means that the pressure at that point maybe it can be 20 times the atmospheric pressure. So in that case, we would use circular pipe. So, and ducts are used when the pressure difference between inner and outer side of the duct is small. Like in air conditioning application, if you have seen it carefully, that the ducts are usually used in air conditioning applications. Why is that? Because in that the refrigerant usually flows through the duct and it hasn't got very high pressure. So it means that the pressure of the refrigerant inside and the pressure which is outside, which is atmospheric pressure, they are normally not very different. And secondly, it is very easy to kind of hang it on some, and aesthetically it looks very good. So that's why we use ducts when we talk about the when we talk about air conditioning and refrigeration application, right? So anything you want to add? Okay, go on. So that's fine. So I have explained that where we use pipe and where we use duct. So difference between pipe flow versus duct flow I have already explained. And then if we talk about the transportation of fluid from for example the underground tank of your in your home to the overhead tank at your roof. So basically we use a pump, but pump is a kind of give energy to the water so that it can flow against the gravity. But there are, you can see that there are piping involved, and then there are certain components which are in addition to piping. For example, there is an elbow here, so it is used to change the direction of flow, and then there is a T-valve. So it means that here the flow can be divided into two portions. One is going into the overhead tank, and the other one is going to outside, and then we can control the volume flow rate through any of these branches by using valves. So valves are something that they are used to control the volume flow rate. Now we can easily see that the piping system which is used, there are basically two types of things there. One is the pipe flow, and then the second one is flow through other components. So other components involve usually pump, turbine, then we have got valves, keys, and then what else? Valve, T, and then elbows, right? So these are the two major components. One is the straight pipe, which we are going to consider now, and then we would also consider the losses which are which the fluid experiences due to passage through these components. So the losses which comes due to friction, they come under the category of major losses. We call them major losses. So it doesn't mean that the value of those losses would always be greater than the losses which are experienced in these components. So, and then the losses through this other components, they are covered in minor losses. So we call them minor losses. Then again, they are not minor, and it is very much possible that these minor losses, the value of these minor losses are greater than the value of these major losses. So major losses are due to the friction or viscosity, right? So they are due to friction, and these minor losses, they are due to the discontinuity in the flow. Like in valves, we reduce the volume flow rate. In T, we kind of divide the flow into branches, and then elbows, we turn the flow in some other direction. So they are kind of producing some kind of discontinuity in the flow. So down the line in this chapter, we would also consider the minor losses as well. And in the beginning, we would focus on the major losses, which is due to friction. So that is the major crux of this chapter, which we are going to cover in the next couple of weeks. Not couple of weeks, maybe more than couple of weeks. So first of all, we need to characterize the flow in pipe. So for that, we know that in terms of flow, we can also characterize it by using laminar, transitional, or turbulent flow, right? So flow can be subdivided in three subcategories. One is laminar, then we have got transitional flow, and then turbulent flow. So for the laminar flow, the viscous forces are greater than the inertial forces. So it means that the inertial forces wants to cause the acceleration or momentum of that fluid, but because the viscous forces are very high, so it means that the flow remains a kind of streamlined flow. In transitional flow, viscous forces are comparable to the inertial forces. And in turbulent flow, viscous forces are quite less than inertial forces. Right? So in transitional flow, there is some kind of random motion, but it reverts back to laminar flow because sometimes viscous forces are dominant, and then it's kind of at some other time inertial forces are dominant. So whenever usually I give an example from a real world problem, like if we have got a society, if we take society as a fluid, I don't know that whether that analogy is very good or not, but if in this society the policing or our paramilitary forces, they act like viscous forces. So they kind of try to maintain the harmony in the society. But uh, uh, at some locations where the policing or paramilitary forces are not present, then there is quite chaos. So it means that those are the regions where these inertial forces are more dominant. So we can see these examples very clearly in our lifetime that sometimes the the policing is not very effective, and then there is some kind of unrest in the society. But in majority of the times we have got quite peaceful society, so we can say that it's kind of laminar situation. So it means that it is kind of very hard society in a pretty much harmony, but sometimes it is disturbed, so it is just kind of creating that analogy. So that this distinction between laminar, transitional, and turbulent flows, that was first reported by Reynolds, that was Osborne Reynolds. He conducted experiments in 1883. So what he did, that he injected a colorful dye into pipe flow and studied the resulting streak lines for different flow rates. So when the flow rates are quite less, it means that the initial forces were quite negligible. Then the streak line remains well defined, straight line. So it means that the fluid particles follow the streak line in a very straight path. But when it means that the viscous forces are dominant over inertial forces. In the transitional region, when the volume flow rate was increased, then we can see that there is some kind of distortion as we move along, right? So it shows slight distortion. For intermediate flow rates, it means that the viscous forces are comparable to inertial forces. And then if the volume flow rate is increased further, then the streak line show high level of distortion for high volume flow rate. So that is the case when the inertial forces or the forces which try to make the flow chaotic or random, they become more dominant as compared to viscous forces which try to make the flow occur in a very streamlined fashion. Right? So these experiments were conducted by Opson Reynolds in 1883. Right? And one thing which I missed on the last slide, that the driving flow forces in the pipe flow, they are either the pressure difference and they are also the gravity. The example of pressure difference, that we need a pump to move the fluid on a higher altitude. But whenever we want that fluid to come into our washroom tap, then we don't need any pump to flow that water, because in that case the water is there is a potential energy because it is at higher altitude. So whenever you open the your tap, then there would be some water provided if your overhead tank has got some water storage, right? So gravity can be driving force, and then pressure difference in normally the driving force in the pipe flows or internal flows. So now if we put velocity measuring probe in this flow, then we can see that time history of that velocity at that location. So here, if you see here, that we have shown the time history of a point velocity in a laminar, transitional, and turbulent flow. For the laminar flow, you can see that the flow velocity remains unchanged at a point, because it is a fully developed laminar flow. So in that case, that if you put a probe at certain point, it would give you the same value of velocity if the cross section of this pipe is not changing, right? And because we are talking about steady flow as well. And then in transitional flow, we would have some kind of fluctuation, periodic fluctuation, and then again it would become straight line, and then there would be again the attempt of inertial forces to dominate the flow. They would do it for some time period, and then again it would become laminar. But if we increase the velocity, then we can see that there is kind of random motion. So in random motion, we have got kind of a mean value we can define, and then there are some fluctuation, the level of fluctuation. So if we increase the velocity more, then these fluctuations would become more. The amplitude of these fluctuations would be more, right? So in terms of, because we are as an engineer, we need to come up with some numbers to make a distinction that whether the flow is laminar or it is in the transitional range or in the turbulent range. So for that we have got a non-dimensional number which is called Reynolds number. So Reynolds number is basically, it is the ratio of the inertial forces to the viscous forces. So here, if we are talking about internal flows, which is this chapter is all about, in that we have got some kind of diameter. For pipe or for duct, we usually use hydraulic diameter. We would come across this and later in this chapter. So velocity into diameter divided by this kinematic viscosity. But if we are talking about external flows or boundary layer flows, then we have got free stream velocity into the length of that surface on which the flow is happening divided by kinematic viscosity. So for the pipe flow, the ranges of the Reynolds number, if the Reynolds number is less than 2000 or 2100, it is characterized as laminar flow. And if it is between 2100 and or 2000 to 4000, it is termed as transitional flow. So laminar flow is this flow, this straight line. Transitional flow, it is this middle line where it has got some intermittent fluctuation. And then If the Reynolds number of the flow is more than 4100, then we can say that it is turbulent flow. But it is only valid for the pipe flow, which is internal flow. When we talk about boundary layer flow, we will see in chapter number 9 that the critical Reynolds number, which was in this case 2100, that critical Reynolds number, that is okay. What is critical Reynolds number? Critical Reynolds number, we usually define it by REC, and we call it critical Reynolds number. And it tells us that the flow is laminar or turbulent. So it means that when the Reynolds number is less than REC, then flow would be laminar. Otherwise, it would be transitional or turbulent, right? And the value of critical Reynolds number for the internal flow, which is pipe flow, that is usually 2100, or we also take it 2000, because the surface roughness of the pipe also plays a role in determining the critical Reynolds number. For the new pipe, it would be 2100, but after some operation like 1 year or 2 years, there would be some sedimentation on the pipe surface, which would have so due to that there would be some roughness on the pipe surface. So then the critical Reynolds number would reduce to 2000 or maybe even 1800 as well. So for the external flows, when we have got a flow over this surface, so if this surface is kind of length L, and then U infinity is the velocity which is coming over this pipe on this plate, then we define Reynolds number for this case as U infinity into length divided by mu, and critical Reynolds number in this case is 5 into 10 to the power 5. It means that up till 5 lakh value, this flow inside the boundary layer, we call it boundary layer, and we would talk about it in detail in chapter number 8. So in boundary layer, to become turbulent, the Reynolds number, critical Reynolds number is 5 lakh, but for the pipe flow, it is only 2000. So it is basically because the dynamics of the internal flow and external flow are completely different. So the value of critical Reynolds number is also significantly different for internal flows and external flows, right? So now whenever there is a pipe flow, so at third there would be always an entrance point to a pipe, right? So it can be the water which is coming into the pipe from the a big storage tank, or it can be through some flow through driving force produced through operation of pump. So in the beginning of the pipe, when the yes, anything you want to add? Usama Aslam. Usama, can you hear me?
Yes, sir.
Do you want to ask any question? Okay. Okay, that's fine. So I was talking about that whenever there is an entrance of fluid inside a pipe, there is a region, there is a length in which the flow is changing. If you see that, let me draw it here. That if this is pipe, so I would also give you we could also give you some introduction of boundary layer. So if we say that U infinity was 10 meter per second, so the flow was coming from here at 10 meter per second, right? Zama, okay. So when it would enter this pipe, it would try to maintain this uniform velocity, which is 10 meter per second. But because we know that there is a condition which is called no slip condition, which means that the first layer of this molecules need to stick with the pipe surface, and it would have the same velocity as of this pipe, which would be zero in this case. So it means that the second layer would experiencing a drag force in the negative x direction, because the first layer that is sticking with the pipe, and then it means that it would apply a resisting force on this drag force on the second layer. So due to that effect, here the velocity is 0 meter per second, but here it would be less than 10 meter per second. It would be maybe it would be 5 meter per second. But when it is reducing in the second layer, in the central layer, it would be increasing, because in order to maintain the same mass flow rate, if at 1 second, if the velocity is decreasing, then at the center where the viscosity effect is very low, the center line velocity would be more than 10 meter per second. Maybe if I draw that velocity profile here, it would look like something like this. That in the center, maybe its value would be 20 meter per second. Uniform value was 10 meter per second, but the center line velocity would be 20 meter per second. Why it is more than the uniform value? Because at certain regions, the velocity here is less than 10 meter per second. So in order to compensate that volume flow loss, the velocity at the mid plane or the center line becomes more. And this drag force, whenever, okay, we say that, okay, let me make a zoom in view, okay. If I show it, only the one pipe surface. So we take locations here. Here we have got location 1, location 2, 3, 4, 5, right? So first of all, we say that at 1, the velocity of the molecule, which is in the second layer, it is 10 meter per second, because it has just entered the pipe. But because from 1 to 2, there would be a kind of drag force on this molecule due to those molecules which are on this pipe surface. So it means that if we measure the velocity of this at point 2, maybe it would be 8 meter per second. And here it would be at point 3, it would be 6 meter per second. At point 4, it would be 4 meter per second. And then at point 5, it would be 2 meter per second. Right. Now, what happens in the velocity in the in the war normal direction? It would increase. Maybe it is here it is 8, maybe here it would be 9 meter per second, and then after sometimes it would have kind of 10 meter per second here, right? Which is the uniform value which is coming from here, 10 meter per second. Similarly, here it is 6, then it would be 8, then 9, then 10. Right? So if I draw a line which is representing 10 meter per second at each location, it looks like this. So this edge, this is called boundary layer. So boundary layer is the distance away from the boundary layer thickness is the distance away from the surface at which the the value of the velocity becomes almost equal to the free stream value, which is coming from outside the pipe. So you can see that the boundary layer, and we represent it with the symbol delta, and we would also discuss it again in chapter number 8. And delta is function of x, and we can easily see that this boundary layer is being growing in the x direction as the flow happens. But after some time, then there is kind of, in this case, for the pipe flow, that the boundary layer can only grow up to the center line, like this. Because there would be a counter boundary layer coming from the top surface, from the other side. So it means that when these boundary layers grow in the internal flow, they can only grow up to the center line, and after that, once they merge at the center line, after that the flow becomes fully developed. So this portion is called entrance region, and after that we have got fully developed region. And in fully developed region, because now there is no change in velocity, because now the velocity boundary layer is fully merged at the center. So it means that in the fully developed flow, the viscous forces are balanced by the pressure drop, which is happening in this pipe, right? So if you see here that growth of boundary layer and a merger of boundary layer at the center line, that is shown by this dotted line, and once they kind of merge at the center, after that the flow is fully developed. So fully developed flow, how can we tell that what is the definition of fully developed flow? In fully developed flow, the velocity does not change in the flow direction. So it means along the streamline. If we follow one streamline, if this streamline has a velocity of 1 meter per second, it would remain 1 meter per second for throughout the pipe until the flow is again gone through any component like valve or T joint or whatever. So up to that point, it would be fully developed, right? So entrance region is where the flow velocity is changing and the boundary layer is growing. And once they are being merged at the center line, after that there is no further growth of boundary layer. And that region is called entrance region, or that length is called entrance length. Right? So velocity of fluid changes in flow direction along a streamline in the flow entrance developing region, and that I have just explained that how in the x direction along the streamline it decreases due to the drag force applied by the layer which is stick to the wall, and it increases in the wall normal direction. So I have just explained this on the whiteboard. So, and then in the velocity of fluid is constant along a streamline in the fully developed region. Why is that? Because the viscous forces are completely in equilibrium with the pressure drop forces in the fully developed region. So if you see that, if we want to know that what is the entrance length, here they have defined it with the symbol LE. So LE becomes equal to LE upon D, which is non-dimensional number, that is equal to, if I can write it here, because that is a little bit very small in the slide. So if I, okay, let me redraw it. So if this is our entrance region, so we define it with length which is LE. And if this is the diameter of the pipe, so we define non-dimensional number which is LE upon D. LE upon D, that is equal to 0.06 Reynolds number for the laminar flow. If the flow is laminar in the entrance region, if we want to calculate the length of entrance region, what we need to do that we need to calculate the Reynolds number and then multiply it 0.06 and then multiply it with diameter. So let's suppose if we have got Reynolds number of 10, so and diameter is 1 meter, then the entrance region would be 0.6 meter because Reynolds number is 10. So the entrance region would be 0.06 into 10, which is 10, which is basically 0.6 meter. But if Reynolds number, if I talk about Reynolds number is like 2000, which is still in the laminar range. So for if the Reynolds number is kind of 2000, then LE would be 2000 into 0.06 into diameter 1 meter. We have taken it, so into 1, so it would be 120 meters. So now you can see that it depends linearly on the Reynolds number, right? For the laminar flow. For the turbulent flow, the dependence of entrance length is a little bit different. So LE upon D in that case is usually that empirical correlation is 4.4 times Reynolds number 1 by 6. Now it doesn't, the entrance length doesn't depend linearly, but it is dependent kind of Reynolds number raised to power 1 by 6. So it is not a very strong function of Reynolds number. That can also be seen here. Here, if you see that this is the plot of LE upon D against the Reynolds number. So in the laminar region, you can see a very linear slope having one. Uh, it means that there is a linear relation between Reynolds number and LE upon D. But here you can see a second curve whose slope is quite less as compared to the first slope. So that is for the turbulent flow, right? And in turbulent flows, either we use this relation or we usually say that 20 to 20 diameter to 30 diameter, we usually take the entrance length as a rule of thumb. And this is the value of entrance length for turbulent flow. So if the flow in a pipe is turbulent, then we can say that initial 20 diameter of that pipe can be discarded uh, as uh, as developing flow, and after that we can say that it is fully developed turbulent flow. So now I think we can have 5 minute break, and then we will conclude the lecture after this. Okay, welcome back after the break, brief break. So we were discussing about the entrance region and how can we calculate the entrance region in the laminar flow and turbulent flow. And because this is only the state pipe which we have shown in the diagram, but in actual system it can be quite complex system. So we can easily see that in this diagram that the water is being taken out of this leather wire, and then it travels along X for certain period, and there is a U-turn, and then it comes down. So we can see that once it enters the pipe in the beginning for certain length, there is an entrance region, right? And then after that entrance region, we have got fully developed flow up till the point the start of this U bend, and then after this U bend, there is a kind of again there is some kind of developing flow in the start, and then fully developed region after that, and then there is another discontinuity that the direction of flow is changed. So it means that this entrance region or developing flow that occur quite frequently in actual systems, and the fully developed pipe flow, it is also there, but the frequency of this switching between fully developed and developing flow is quite significant due to the use of different components in the piping system, right? And then now the last thing about this topic is that how the pressure gradient and shear stress, they are interrelated in the entrance region and in the fully developed region. So in horizontal pipes, the main driving force is pressure difference. If it is kind of at an angle, then there would be a component of gravity as well. But for the simplest case, the pressure difference is only the driving force, and the viscous forces, they are the major forces which opposes the driving force. So the viscous effect causes steady flow. So it means to say that in the fully developed flow, there is an equilibrium between the pressure difference force, which is the driving force, and the viscous force, which is the retarding force, or we can say that opposing force here. So that is why the particle in a certain streamline in the laminar fully developed flow, they would have the same velocity along the streamline. So, but in the entrance region, because the pressure difference, there is also some variation in velocity. So it means that now in the entrance region, pressure forces, inertial, there are three forces. One is pressure difference force, then there is the viscous force due to viscosity, and then inertial force, which comes due to change in velocity along the streamline. So you can easily see that the pressure drop in the entrance region is high as compared to the pressure drop in the in the fully developed region. So while that, if we look at the velocity profile in the entrance region, because let me explain it from here, from this figure, that in the entrance region, because if I say that uh, after point 5 it is fully developed, and up till 1 to 5 it is entrance region. Now here, that if we calculate the wall shear stress in the entrance region, we know the formula tau omega, that is equal to mu into du upon dr. Dr or dy, if we are talking about simple flat plate, we know that du dr at R is equal to capital R. So it means that this is the at the pipe surface. So if you look here, the value of du upon dr, that is maximum at the entrance, because the velocity is maximum between first and second layer of the molecule, and this du by dr decreases as we move down, because now 8 minus 0, here it was 10 minus 0, here it is 6 minus 0, 4 minus 0 and 2 minus 0. So this tau omega decreases along x in the entrance region, and its value becomes constant in the fully developed region. So because the tau omega is the maximum at the entrance region, so it means that the retardation force is, or the causing force is maximum at the entrance. So that's why to drive the flow through that maximum resisting area, the pressure drop would also be greater. So you can easily see that the pressure drop in the beginning is very high, and then that slope becomes almost equal to a constant value in the fully developed case. So that is the deviation from the straight line. I have just explained that because the wall shear stress is very high at the beginning due to increased value of velocity. So that's why pressure drop is also high in the entrance region, right? And in the fully developed region, the pressure drop is constant. And if you remember in chapter number 6, when we were deriving the relation for the Poisson flow and Couette flow, in that we wrote delta p by delta x is equal to minus delta p by L, where L is the length of this pipe, and then delta p is the pressure drop in this pipe. So pressure varies linearly in fully developed region due to viscous effects, and shear stress in the laminar flow is the result of random molecular motion, which is depicted by this relation. Tau omega is equal to mu du by dr, and in the turbulent case, it is macroscopic level due to the random motion of the fluid particle, right? So that is the macroscopic phenomena in case of turbulent flow, but in case of laminar flow, it is microscopic phenomena. It means that it only depends upon the viscosity here. But in the turbulent flow, it also depends upon the random motion of particles from one streamline to other streamline, in addition to the viscosity effect. So now we need to derive the relation of this. We need to derive the relation between velocity. Okay, let me write velocity, shear stress, and pressure drop in fully developed laminar pipe flow. So now that is our objective, that if we know the pressure drop, or then how can we calculate the shear stress, which is the opposing force in that fully developed flow, and in addition, more importantly, how can we determine the velocity due to that applied pressure drop. So that is the objective here. For that we need to do the infinite decimal analysis as we did in chapter number 6, and we would be doing quite a bit of derivation. So please concentrate and ask questions where you don't understand the derivation. So we consider a fully developed steady laminar pipe flow in a horizontal direction. So it means that there is no gravity force involved here. So because we are talking about laminar fully developed flow, So it means that local acceleration is zero because it is steady flow, and then convective acceleration because partial u by partial x is equal to zero because it is fully developed. So that is the definition of fully developed, that the along a streamline the flow velocity does not change. And then it means that there is no acceleration, so the pressure force is balanced by the viscous forces in the fully developed region. So because if there is a net force, then only then there can be acceleration, because we know that F is equal to ma, and F, that is kind of net force. So if net force is zero, the acceleration would be zero, but the flow would be happening at a constant velocity value. So every fluid particle moves along the same line with the same u velocity and v and w velocity, which are in the other direction, velocity component, they are zero. So pressure variation, it is non-zero negative pressure drop in the x direction, because we all know that the flow only occurs if we go from left to right. If we have got high pressure on the left hand side and on the right hand side we have got low pressure, so only then the flow would occur in the positive x direction. And then there is no pressure drop in the radial and circumferential direction, so that's why v and w, they are zero. So we consider a fluid element in a pipe at time t. It was a rectangular component, but after some time t plus delta t, it has got attained a cylindrical shape. While that, because there is some kind of shear force happening on this element surface, because there would be some other element. So we are talking about this because we are seeing the front view, so we are seeing it like a rectangular component. But if we see from this side, then we would see a circular cross section, because we are talking about a pi flow. So after some time t plus delta t, it would take a cylindrical shape, because there would be some shear force applied on this fluid element by the next element which is on top of it, right? So if we do the balance of forces here, so in this case we have got the length of the element is small l, and then here we have got r, which is the variable radius here. So there are two types of forces on this element. One is the pressure force, which is driving force, and then the shear force, which is acting on its surface. So if we show the force balance, we can see that on the left hand side of this element we have got pressure P1, and then if we want to make it force, we need to multiply it with the area on which it is acting. So because as I have already explained that it is a circular element, if we see from this side, so because its radius is r, so the surface area or cross sectional area would be pi r square, which is written, maybe I need to zoom it a little bit. So now maybe it is a little bit more visible to you. So here we can see P1 into pi r square. So pi r square is the cross sectional area at this, and then because on the right hand side, if delta P is the pressure drop here, then the pressure on the right hand side surface, which is in the negative x direction, because pressure is always a compressive force, P1 minus delta P. So delta P is the pressure drop occurring through this length L into pi r square, and then there would be a resisting shear in the negative x direction, which is tau, and because it is acting on the surface of this element, so surface area of this cylindrical element would be 2 pi r L. Right, so because we know that the surface area of a cylinder is 2 pi r L, so the third dimension, which is into the board, that is kind of circular cross section. So let me draw it here. Maybe it would be. it is just kind of, this element is something like this. Right, so this length is, and this is, okay, only this thing is r, which is radius. And because shear stress would act on the surface, and this is r again, so here it was P1 into pi r square, and here the pressure drop is delta P. Delta P is the pressure drop, so it means that the pressure here would be P1 minus delta P, and then pi r square, and then shear force is acting in this direction tau into 2 pi r s, which is the circumference for the cylinder, cylindrical element, right? So I hope that this point is clear. Then if we apply the energy balance, we can write P1 pi r square, which is in positive x, then these are the two in the opposite direction. So now we can see that P1 and P1 pi r square would be cancelled out, and we are left with delta P pi r square is equal to 2 pi r n. So let's do it here. So if we write delta P into pi r square is equal to tau into 2 pi r n. So if we kind of do the simplification, so we can write delta P upon L, and then this r would be cancelled with this r square, pi would be cancelled with this pi, and we are left with 2 tau upon r. So this is the relation of pressure drop and shear stress, right? So now in most of the cases that would happen that this delta P we know from the pump which we have installed. This delta P upon L is known, so we can write that tau becomes equal to delta P upon L into R upon 2, right? So if we see here that if we want to calculate that what is tau in terms of radius, so because radius, as I have just explained, that it is a variable value, so tau would be equal to delta P 2L into R, and then we can call it C into R, and C is equal to this, which is a constant value. Get delta P upon L, that is known by the pump we have installed, and 2 is also constant. So if we want to calculate the value of tau omega from here, what is the value of C in terms of tau omega, we can easily do it, because we know that in in this figure, R is equal to 0 at the center line, and R is equal to capital R at R is equal to capital R at the pipe surface, and tau would be equal to 0 at this at the center line, and it would be equal to wall shear stress at the pipe surface. So if I put at R is equal to capital R, which is the pipe surface, tau is equal to tau omega. So from here I can write that tau omega is equal to C into R, and C would be equal to tau omega upon R, and we can also write it tau omega 2 tau omega upon C, right, in terms of diameter. So that's what I have written here. C equal to 2 tau omega upon D. Now, if we put this value here, then we can get the value of tau in terms of tau omega. If we put this value here, 2 tau W upon D into R. So that comes out. So tau comes out to be 2 tau WR upon D. So let's take this relation. So if we take just a minute. So let's put it there. So we have got this relation now. The second relation we know that is delta P upon L, that is equal to 2 tau upon R, right? So now if we want to write delta P in terms of tau W, what is tau W here? Again, I am telling you that is wall shear stress. Wall shear stress, and that is equal to mu into du upon dr at r is equal to 0. So now if we put this value here, so we can write delta P upon L 2 into 2 tau omega r upon d upon r. And then you can see r would be cancelled out with r, and this 2 to 2 would be 4, and then delta P can be written as 4 tau omega into length divided by diameter. So this is the relation, first relation we have got, that is the delta B in terms of tau omega. Before that, we have also got the relation of delta B and shear stress at a fluid element, but now we have derived a very significant relation of delta P in terms of wall shear stress. But even now, we don't have the velocity information in these two equations. So, in the next class, which is on Friday, we will see that how the velocity should be there. So, if we need to get the velocity here, then it is very easy that uh, we can use the relation which is shown here, and then we put tau is equal to minus mu du upon dr. Minus is due to, because the this is the kind of resistive force, so that's why we put minus here. So we can now we can relate tau with velocity here, and then we can also relate tau omega and delta p with tau. So we can after that we need to do a little bit of integration, and then those steps we will complete it uh, in the next class. So is there any question from this class? We have just did the half derivation. The rest of the derivation will be completed in the Friday's class. Yes. So it seems that there is no query at the moment, so that is okay. So